broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, and thank you for joining us for today's webinar, OLED Pixel Measurement and Correction. We appreciate you taking the time to be here. My name is Shana Warner, and I am the Creative Marketing Specialist here at Radiant. I have the pleasure of introducing today's speaker, Alex Podschwitt, who is a Level 2 optical software engineer. He works on Radiant's application engineering team, and he has a lot of experience working in OLED display applications and develops and supports software applications to characterize emissive displays, projectors, LEDs, and more. Alex has dedicated the past 4 years at Radiant building expertise in light measurement and continues to educate new users on improving measurement acquisition techniques through a fundamental understanding of light principles. Alex received his Bachelor of Science in Physics and Applied Mathematics from the University of Washington here in Seattle. So before we begin, I want to go over a few housekeeping items to keep in mind during the broadcast. Our presentation today will last roughly 30 minutes, during which time you're welcome to ask questions for our presenter to answer at the end. You could do that using the questions window in the GoToWebinar interface. Typically that's located on the right side of your screen. All of our questions will be queued and answered by Alex following the presentation, but feel free to ask a question at any time. So now without further ado, I'll hand things over to Alex.
Thanks a lot, Shana. My name is Alex Podschwitt, and as was mentioned, I'm a software engineer at Radiant Vision Systems. It is great to be here with you today, and I look forward to sharing with you the current state of OLED display measurement solutions at Radiant Vision Systems. Let's start with who we are. We are Radiant Vision Systems, a world leader in light and color measurement, and we have been providing scientific-grade measurement solutions for nearly 25 years. We are excited to get to share with you some details regarding our solution for correcting luminance and color of OLED displays at the pixel level, which we will refer to as our OLED Demura solution. Today we will begin talking about the rise of OLED in display. Then we will move into the inspection challenges faced with OLED displays. Next, I will introduce methods for pixel level measurement of these displays, and I will wrap up the talk with an introduction to our pixel level correction solution utilizing our imaging colorimeters and analysis software that I have developed over the past 4 years at Radiant Vision Systems. Let's get started. Our webinar today is focused on organic light-emitting diode display technology, which has been applied to various fields such as smartphones, tablets, television, augmented and VR applications, and smartwatches. The development of display technology has been rapid over the past few years. There are some key changes: increasing size, higher display resolution, higher quality display technology, unique shapes, and the growth of microdisplay for AR, VR. These requirements grow the need for a sophisticated inspection system that meets takt time and accuracy requirements to measure these pixel-dense displays. There is a growing need for inline automated display correction built on top of the inspection system that we provide today. Let's begin by exploring OLED inspection challenges. Each pixel of OLED is an independent emitter as shown on the left. What we mean by a pixel is any of the red, green, or blue pixels in the image. OLED displays require us to evaluate each pixel for failures. During the manufacturing process, things can go wrong. Bad pixels, dead pixels, and non-uniform pixels can exist, which are hardly detectable by a human inspection process. Compared to previous technology, LCD itself has a backlight and unique filters to show the color and luminance. This is not the case for OLED pixels. They exhibit pixel level variation, color dependence on brightness, and non-uniformity known as Demura at low gray levels. We will begin by looking at a raw image of a white OLED display. So what's wrong with this display? The first thing that we can notice is there's some pixel level noise and variation on this, and a few dead or dim pixels compared to the background. There's a systematic rectangular grid on this measurement that goes horizontally and vertically. And in the lower right-hand corner, there's some region that is darker than the background, and that would be what we would refer to as Demura on the display. So let's begin by looking at pixel level variation. At high gray levels, a bright display, there's strong pixel level variation which can be noticeable to an observer. The chart here represents the luminance variation of a row of pixels on an OLED display. And the image here is a one-to-one representation where each measurement pixel represents the luminance and color output of a display pixel. For this, we can observe about an 8 to 10% variation across this row of pixels on the OLED display. Next, let's look at color variation over gray level. And just to tell everyone, this was the predominant issue for the horizontal and vertical grid regions on the example measurement 2 slides before. The figure on the left shows normalized luminance output of a display. This measurement was taken over many gray levels, characterizing the response of each pixel. The nonlinear response of the pixel over gray level, known as gamma for the R, G, and B pixel in the display, is different in this case. The effect of this is the figure on the right, which shows how a relative small variation in the output of the R, G, and B pixel can cause the white point to change with respect to gray level. As a pixel in an OLED display is independent of neighboring pixels, this should be characterized over many gray levels to characterize the response of all of the pixels within the display. Finally, we can look at Demura on an OLED display, like what we saw in the lower right-hand corner of the example measurement. This plot here represents the relative luminance difference between a row of pixels on an OLED display. At the left-hand side of the plot, you can see that the relative luminance variation between a pixel and its neighbor changes as a function of gray level. This motivates the need to characterize the luminance output as a function of gray level. This plot demonstrates some of the at high brightness levels, we can see that the overall uniformity of the display, looking at the max pixel for this row and the min pixel of this row, is about 90 to 95% at peak output. When we go down to a gray 32 level, this uniformity metric drops to 30 to 40%. It is the goal of our inspection system to characterize the response of these pixels and provide a correction that can capture this. So we have identified what we are looking for and why we are looking for it. So what is the motivation for correcting OLED displays? The first is that we can improve yield. The more displays that are corrected, the more product that is produced, the greater a supplier's competitive advantage. The next is that we want to limit waste due to inevitable quality issues. All OLED displays exhibit some level of pixel level variation. Some of these displays can be corrected, reducing scrap materials. The final item we want to do is safeguard efficiency. Automated inline OLED correction solutions keep manufacturing processes moving despite inherent quality issues. In the next section, we will discuss how we can perform OLED display inspection. Let's get started by introducing the materials and method needed to perform pixel level characterization. Automated visual inspection, also known as AVI, is a testing and rating technology for flat panel display, mainly composed of an imaging colorimeter and analysis software. It can completely replace human inspectors. In manual detection, the results of two operators may be inconsistent. With an imaging colorimeter and automated visual inspection, we can establish a unified pass-fail results. A high-resolution sensor is needed for this pixel level measurement. Being able to measure high pixel count displays requires an equally high pixel count sensor. For example, our 29 megapixel sensor shown in the upper right-hand corner of this slide can be used to measure up to a full HD screen or 1920 by 1080 display pixels. Alternatively, a low-resolution CCD sensor being used to measure a high-resolution screen can result in relatively high measurement errors. The image on the right in the center shows aliasing, which is an artifact of this. This aliasing can cause errors up to 10% or higher when attempting to estimate the luminance of an individual pixel within the display. Earlier I mentioned a big trend in display technology is increasing pixel density, count, and size. This will lead to situations where the display resolution is greater than 1920 by 1080. For this, we will introduce measurement techniques where we cannot achieve the resolution requirements specified. For this, we can take two approaches which we will explore. The first is to combine multiple imaging colorimeters together, or we can simulate multiple low resolution screens with a single imaging colorimeter. This solution, as the schematic in the right-hand side, is a proposal for utilizing multiple 29 megapixel CCD cameras to measure the same display. Other configurations are possible depending on the size of the display, such as imaging quadrants of a large format OLED TV. Radiant TrueTest software combines the measurement results of these independent captures, post-processes them, and factors this information into a single synthetic measurement representing the luminance of every pixel within the display. And to reiterate, when we talk about synthetic measurements, we're talking about one measurement pixel, such as the image in the bottom of the slide, representing one display pixel. The second method is known as space pixel measurement, which is capable of measuring a 4K or even 8K display only with one 29 megapixel camera. In this measurement, as the resolution of the camera is not high enough, it is impossible to measure the full screen with only one measurement. By spacing out the display pixels, we are able to get enough CCD pixels per display pixel to get a high accuracy measurement of each pixel. To contrast this to the previous method with 3 cameras, now more measurements need to be taken sequentially compared to the parallelized image capture in the previous technology. no matter multi-camera or single camera, the ultimate goal is to measure the luminance or color value of each pixel accurately, then combine them into a final synthetic measurement. The software processing is the same regardless of the measurement process it came from. So this slide will demonstrate a two-camera approach of imaging a single display. First, we start with the raw measurements, where we have to first locate the display pixel within the image. And that is what represents the red border around the two raw images. From the found locations, we synthesize that to two separate synthetic images, which would effectively be at half of the resolution of the initial display. Finally, we will what we call concatenate the images, or just simply combine them on top of each other to provide the final image that represents the luminance and color variation of the entire display. The first step is to locate the displays in the camera image. The red circles on the right are known as a region of interest, and each display pixel will have a region of interest centered over the pixel. The registered location of the pixel is stored for reuse and rapid data extraction at future steps. In this example, a given display pixel is sampled with an 8x8 circular region of interest. The next practical concern is where are the other pixels relative to each other, and how many are there? As you can see, for many OLEDs, there are many configuration schemes. And it is not always true that the logical resolution of the display, such as QHD 2560 by 1440, has an equal number of red and blue pixels compared to the green pixels. That would be the example for what we've called OLED phone 1, 2, and 3. Regardless of the varying pixel layouts on the OLED display, the software can auto-register the pixels. The synthetic measurement of a display will be at the resolution of the display being measured, although the resolution of the CCD camera used is much higher. For a full HD 1920 by 1080, the resolution, while the resolution of the 29 megapixel CCD is 6576 by 4384, the full HD screen would be 1920 by 1080. So the synthetic image will be ultimately at the resolution of the display. What this does allow is a simple pass-fail detection based on dead pixels. The image on the lower right here represents a pixel in the synthetic where it is dead compared to its neighbors, or much dimmer. The above plots represent synthetic measurements across different devices and does a comparison to traditional LCD technology. For OLED, there is an interesting deviation in the amount of high-frequency luminance variation at the pixel level. The variation for the OLEDs is approximately 5 times greater than the LCD phone, which is at 0.61% when the OLED phones are sometimes almost up to 3% variation. Another interesting effect is that the overall color variation over all of the pixels in the display is much higher than that compared to the LCD phone, which we could see that the chromaticity X and chromaticity Y, which are the standard measurements of color for an OLED display, are almost 5 times greater than the LCD display. The measurement results show the measurement of the luminance and color of each display pixel with high accuracy and identifies bad pixels of the display. These with insufficient luminance or those with some problems. These pixels can be identified by setting different pass-fail criteria and the exact pixel coordinate column and row within the display can be returned as a result. The representation and use of a synthetic measurement and measurements over many gray levels allow additional, what we will propose soon is the Demura solution to create correction coefficients. The left image represents some actual OLED display prior to correction. One can note that there is some sort of color variation on the image, and after the correction process and after measurement, we greatly reduce any color variation of the display. Let's get started by introducing our pixel level correction using Radiance Demura solution. So what is Demura? When an OLED is driven to the same test brightness, the residual effects, as we talked about before, the pixel level variation, color variation dependence on gray level, and Mura at low gray levels can be removed with software processing known as Demura. The word Demura is describing a process of removing Mura from the display. Remove the Mura. Demura. The following section introduces an inline process. The first step is to use an imaging colorimeter to measure the display pixels. To evaluate and quantify pixel uniformity issues. The second step is to measure this pixel response over many gray levels to characterize the Mura at low gray levels that can be present there, which are not present at the high levels, and ultimately build a coefficient that characterizes this response. The following is a schematic of an inline inspection systems. Traditionally, we'd be responsible for 2 fates of the display, a pass and a fail result, based on an initial measurement. Based on those results, the failing displays will have to be scrapped, while the passing displays are okay to ship right away. The introduction of a Demura process allows for a third fate where additional measurements can be taken and attempt to repair optical issues with the display with the Demura algorithms can take place. If these displays pass this process, these displays also could be okay to ship. The requirements for the Demura station on the line include a measurement system, which we have already introduced to be a radiant imaging colorimeter or imaging photometer, measurement software, a calculation of a correction coefficient, which we'll discuss in a second, and then transferring this data to the OLED screen controller. This correction process requires high measurement accuracy, repeatability, and a careful definition of what performance you're trying to get out of the display, and compensation for the pixel and measurement geometries, as well as adjustment for human visual inspection. Radiant provides the measurement solution for Demura applications with sufficient resolution, dynamic range, and software flexibility to acquire OLED pixel data regardless of display variation. Radiant TrueTest software offers a number of powerful features that apply to OLED measurement and are ideal for OLED applications. First, the method to process pentile, which is the distribution of subpixels. Second is to remove any systematic errors introduced by Moiré or aliasing. Third is the introduction of gray level coefficients that vary based on the input level. And finally, to ease integration for production lines, we support a fully documented API. Here again we see the variability of OLED displays from device to device. Using TrueTest Demura, we can easily and automatically set ROIs for each display pixel. The OLED pixel correction procedure utilizes a high-resolution imaging colorimeter. The image on the right was captured with a 29 megapixel imaging colorimeter. The first step, as we had talked about, is to locate the subpixel within an image of the display. Again, the yellow ROI represents the location of the pixel within the display. The next step is we will average the signal over that ROI to compute the luminance and color output of that pixel. We will perform this process for many gray levels to build the pixel response over gray level. Based on the response of the gray level, or based on the response of the pixel over gray level, we can compute a correction factor that will perform a uniformity correction for all gray levels. TrueTest Demura supports automatic removal of the Moiré pattern. The image on the left before Moiré removal shows systematic errors that can be due to the display resolution, the imaging colorimeter CCD resolution, optical lens design. The presence of these issues would not make a practical measurement of the pixel. This effect should be removed. And this is largely achieved through software. And we can see the results of the Moiré removal in the right-hand side where there is minimal systematic errors, allowing us to accurately estimate the luminance of each pixel within the display. Here is an example of the software calculation of the measurement of the pixel and the effect that the correction coefficient is attempting to produce. The light blue curve represents the expected response of the pixel. Ideally, we want all pixels in the display to share this response. The red X's represent our measurement points. So there is some error and some deviation in which we have to correct on a level basis. One coefficient, one correction factor will not work for this type of behavior. And the green arrows show the action that the correction coefficient is making to drive the display to the expected curve. An OLED display typically requires luminance-only correction. The 3 subpixels have a correction coefficient. A pixel has 3 correction coefficient, which in simple terms means that after a video input signal is given, an RGB signal of 20%, we simply scale the signal out by a known value, and that is our correction coefficient. The difference for Demura is that depending on the input level we're trying to drive the pixel to, that coefficient and that scalar will change as well. Let's talk about the results of Demura uniformity improvement. In this example, we see that the red pixels in the display on the left, and this is a synthetic image, show some horizontal and vertical banding and some low, Mura towards the top of the display. That's symmetric on the left and the right side. After the correction, we can see that overall that the banding is removed. The Mura that we were talking about is also removed. And interestingly, for this gray level, the luminance output has actually been increased. And you can see that by looking at the scale of the image on the right-hand side. On the left, the maximum is about 1.3 candela per meter squared. And on the right now, we are up to 1.7 or 1.78 candela per meter squared. For the green pixel, we can again see similar banding effects and maybe a vertical gradient where the bottom of the display is dimmer compared to the top of the display. Again, we can see the removal of this gradient and the Mura. And again, for this gray level, the luminance has been increased for this display. Again, a different distribution for the blue pixels. Potentially a left to right gradient is stronger here. And we can see similar improvements to the uniformity in this example. And finally, for this display, this was a RGBW display, so we had a white subpixel as well that we were attempting to correct. Again, we can see many of the visual artifacts before correction have been removed after correction. Finally, here's another example for a large format OLED TV. Here there's strong vertical banding as well as some line defects. Vertical line defects that we can see towards the right third of the display. Again, after correction, we were able to remove these effects. In summary, pixel level correction has direct positive impact on yield of advanced high-resolution OLED displays. This is very important for the field of OLED because each pixel is an independent light emitter , which can behave and age differently than its neighbors. To perform pixel level measurement, a colorimeter with high resolution and high signal-to-noise ratio is critically important. A Demura solution can be established in line to measure and route devices based on the severity of Mura and apply corrections to the fixable devices, reducing waste. All right.
Thank you, Alex. At this time, now that the presentation has come to a close, we understand we're a little bit past a half an hour and appreciate those of you who've come who have to depart. But for those of you that have asked questions or would like to submit questions, we are going to begin our Q&A session with Alex. We welcome you to send those questions through the questions window on the GoToWebinar interface, and you'll find that typically on the right side of your screen. Just type in a question and we'll queue those and answer them here live. Just to get started, I see a couple questions on whether attendees will be receiving the recording of this presentation following the broadcast. And yes, we will be emailing everyone a link to the recording following today's broadcast, so keep an eye on your inboxes for that. And now I'll let Alex take a look at the questions and answer them as they come in.
Okay, we have a question regarding flexible OLED display technology and how a measurement would occur for this. So for flexible OLED measurements, the measurement would need to occur on a flat surface compared to traditional measurements. The Demura process would have to occur on the pixel level. There's another question here. Is a Mura defect caused by non-uniform display luminance? A Mura defect is more caused by a non-uniform response to the pixel over gray level compared to the surrounding pixels. That is why it is important to characterize the response of every pixel within the display to drive them to the same correction curve. We have another question here regarding how many gray levels are used to measure the pixels. Typically, measuring 6 to 8 gray levels per pixel is required, and this inspection process typically takes around 1 minute. There's a question here about outputting measurement data for each pixel from the software. This TrueTest Demura is built on top of our TrueTest software package, so it supports CSV export formats that can be easily imported into additional analysis software such as MATLAB and Excel, and things like this. There's a question here regarding what kind of system do I need to apply the correction coefficients to the display. Applying the correction coefficients to the display requires specialized Demura IP or an electronic chip to perform the scalings based on the video signal at runtime. There's another question here regarding, can the system respond quickly enough to be used in OLED display mass production technology? As we have seen in our experience, yes, the system responds quickly enough to be used in OLED display mass production testing. There's a new question here regarding how can this be applied to a curved display, particularly with some models of cell phones with rounded displays near the edges. For a curved display, since we register on each pixel independently, the only information we would know is when we register from pixel to pixel, we know the exact coordinate of that pixel within the display. So if there are pixels missing from a rounded edge, for instance, we would just need information about the shape of the display and a map of the pixels to either ask for information here or not. There's another question here regarding how do you ensure that the pixels of the camera correspond to the display pixels? As we know the exact position of the pixel within the display, we can effectively locate a corner of the image and count the number of pixels over as a user-provided parameter. There's a question here regarding, does this method work for correcting color uniformity? As we are correcting for our goal is to drive the red, green, and blue pixels to have the same response. Inherently, we could correct for a color uniformity caused by pixel level variation. If we measure the native colors of the red, green, and blue pixels, we can make sure that the overall color of the display is driven to a specific white point. I think we have, Shannon, we have time for one more question. Is that fair?
Yeah, let's do one more and then we'll wrap up. We're getting a little bit closer to 1:45.
There's a question regarding the calculation of correction coefficients. For Radiant has historical experience in LCD Demura applications since 2006. For LCD Demura, coefficients were more of a zonal correction, while for OLED displays, the correction is based at the pixel level. So there is a correction coefficient per pixel.
Great. I think I see there are still a few questions out there, but I see we're about quarter to the hour, 15 minutes past our presentation time, so I want to let you guys go. Thank you very, very much for taking time out of your busy schedule today to join us. Thank you, Alex, for the presentation. And if you have further questions, please feel free to reach out to our team at info@radiantvs.com. You can see it at the bottom of your screen there. We'll go ahead and leave that up for a couple minutes so you can get that information. Again, thank you for joining us today. We hope you have a great evening, morning, afternoon, whatever time it is where you are. Thanks again and have a good one.
Muted.